your audio, start video, and there I am. Hey, I've got Mark, one of my students. Let's see if I got anybody else. Okay, ta-ta. Okay, well, let's see if I got any customers here. Oh yeah, hey, I think we can have a class. Can you guys hear me? Somebody say hi.
Hello.
Hey, hello. I tell you what happened. Somebody must have run into a power pole because I haven't had any electricity at my house, and I couldn't connect with you guys. Might be nice if I could plug this in. Plug this in. I don't know if you guys can hear me. Let's see, today's Monday, and we're getting a late start. Yeah, but we've got some customers here. Great. Yeah, excellent. And maybe we can have a class. That'd be nice. Yeah. Well, I wonder if you guys can hear me. Somebody say hello. How about Ashley? Ashley, can you hear me?
Yes, I can hear you.
Oh, wonderful. Hey, I think we can have a class. I've had electricity out in my neighborhood, and that's what happened. There's no electricity, there's no internet, no nothing. And so we're running a little late. I graded your tests. I graded all of your tests, and the grade should be on Blackboard. And let's see, wonder how you guys did here. Let me look and see. And I put the key on Blackboard, so you can look at the key. Gee, I can't find it right now. Anyway, there's some people did really well. There's a 90 and a 95 and a 90 and a 90 and a 95, and then there's an 83, an 87, and there's a 73, 74, 74, 74. Anyway, there's all kinds of grades there that you guys did on your test. I can't find it, but the key is on Blackboard. You can look it up. We need to get going here because we've lost some time because of the power outage. And the topic today is we're entering the exciting world of rigid bodies. Chapter 16. Rigid bodies. Today is Monday, right? Is it the 19th? 19th of October. We're in dynamics, and the topic is rigid bodies. And it turns out there's three kinds of motion of rigid bodies. There's pure rotation, which we're going to study today. And then there's pure translation. We've already studied that. We've studied pure translation. And then what you haven't studied is the combined. I think the book calls it general motion. I think that's what they call it, general motion. And see, there's three kinds of motion of rigid bodies. And then after we study motion, they have a fancy name for it. It's called kinematics. I wonder if anybody's electricity went out at their house. Probably not. This is probably just a neighborhood thing. How about Braxton? Unmute and say hello, Braxton.
Hello.
Hey, did electricity go out at your house?
No, everything's still working, so.
I think it's a local thing. It's just in my neighborhood. Somebody took out a telephone pole, I think. Okay, well, good. That's what we're going to do. And then, see, we've already done this. In fact, I'll write the equations for you. There's this one here. You guys remember these. And then there's those constant acceleration equations. They go like this. I wonder if all that's coming out where you guys can read it. Maybe, barely. Okay. Yeah. We've already studied that. See, that's what all this stuff is. It's pure translation. We've studied that. But today we're studying pure rotation. And the equations for that are very similar. But instead of linear velocity, it's angular velocity. And instead of the change in linear distance, it's the change in your angle, your angular displacement. And here it's see, this is linear acceleration. This is angular acceleration. It's a Greek letter alpha. Can you read my writing? It's a Greek letter alpha. And instead of the derivative of linear velocity, it's the derivative of angular velocity. And the same thing here. See, here's linear acceleration. This is angular acceleration. This is linear displacement. This is angular displacement. Linear velocity, angular velocity. The change in linear velocity, well, this would be the change in angular velocity. And same with all of these equations. This one would be like this. See, once you get the hang of it, I bet you could write the angular, the rotation. See, what we're doing is we're writing the equations for pure rotation. And I bet you could write these for this one here. This is the change in linear displacement. I'm going to give you 30 seconds, and I want you to scribble down the pure rotation equations for those. See, you know and love these. Go ahead. I'll be quiet, and you write those equations for pure rotation. Go for it. And then I'll pick on one of my excellent students. And then we'll work some problems. That would be good. Okay, let me pick on one of my students. See, we're in chapter 16, right? Yeah. We're in chapter 16. This is chapter 16. Okay, I'm going to pick on Stuart. Stuart, you're a good sport. Unmute and say hello, please, Stuart.
Hello.
Stuart, did you attempt to write this equation in pure rotation form?
Yes.
Go for it.
Is it delta theta equals omega naught t plus 1/2 angular acceleration t squared?
That's it. Jolly good, Stuart. Stuart, tell me what you wrote for this one.
Omega squared minus omega naught squared equals 2 angular acceleration delta theta.
Good going, Stuart. He's got the pattern there. Well, now we have the equations for pure rotation, and we can do problems now. So let me clear the board here and get rid of all this stuff, if you guys understand that. Now, I had an eraser here, dang it. Oh, there it is. Okay, I'm going to make some room, and we're going to use these equations. See, if you're familiar with these equations, these are pretty easy to use or to think of. Now there's a catch, and you guys know that. The catch is these equations here all of these equations have a skull and crossbones on them. You got to be careful about using all of these because all of those are what they call constant acceleration equations. And if you don't have constant equations, you can't use them. So here we can put a happy face on all of those equations, but on this one here, you don't have a happy face. You have a skull and crossbones. You got to be careful about using those. They don't always work. Okay, well, good. Let's do a problem. Unless you have a question on anything. Anybody have a question on anything? All right. Well, I'm going to erase all this here. And we're going to work problems now. But you can see where we're headed. Once we have mastered pure translation and pure rotation, then we get into the really exciting stuff. General equations. See, because like a car going down the road, it's got both. It's got translation and rotation. Like when you turn and you make a left turn, that the car rotates. It kind of turns through an angle. And so you have both translation and rotation, and that's called combined motion or general motion. That's where we're headed. But first, let's work to some pure rotation problems. Now, I thought we'd do 1613 together. And we will try to get this lecture on YouTube for those that got fouled up because of the power shortage there. What we've got here is a bus engine with belts and pulleys. And now this one's got pulleys, and I'm going to show you how pulleys work. But the engine is pulley A. So let me draw that. This is pulley A, and it has a radius of 75 millimeters. And see, it comes up here. And there's a belt. See the belt? And it turns a little pulley that's got a radius of 25 millimeters. That has a radius of 25 millimeters. And it's fixed or welded to a bigger pulley like that. And it has a radius of 100 millimeters. Now there's another air conditioning pulley, but we'll get to that. Let's one thing at a time. Now here's how pulleys work. The velocity of this belt, now this thing here is turning. Let me read it here. The engine turns at 60 radians per second. They didn't say which direction. We'll just say it's clockwise. We'll say that this is turning at 60 radians per second. That's what they said. Now the way it works is this pulley is going this way with a velocity equal to r omega a. But you know what? That same belt has to have the same velocity here. We ought to call it v sub a. That'd be a good name for it. That's the velocity of that belt. And you know what? That same belt has a velocity here of v sub a. and it goes around this little pulley here, and it has the same velocity here of V sub A. It's got to have the same velocity because it doesn't stretch or shrink. It's a belt, and it's just going around and around, and the velocity is equal to R omega. Now that equation came from this equation here. This equation is called the arc length formula. It's the arc length formula. And if you take the derivative of it, you get ds dt. R is just going to be a constant, and you get d theta dt. You've got the velocity, ds dt, that's the velocity. And that's equal to R omega, because omega is equal to d theta dt. See this equation V equals R omega. It comes from the arc length formula that we know and love. If anybody needs me to explain the arc length formula, I'll be glad to. Just speak up. But remember, there's a catch. This theta has got to be in what? Let me ask one of my excellent students here. Shane, unmute and say hello, Shane, please. Uh-oh, coffee break. Ryan, unmute and say hello, please.
Hello.
Yeah. Hey, Ryan, this theta, it's got to be in what?
Radians.
Yeah. Good going, proud of you. It's got to be in radians, or else it doesn't work. And so see this, when you take the derivatives, what you get is radians per second. Okay, now that you understand that, good. Any questions so far? All right, well, if we understand that, here's the beautiful thing. The velocity of that belt there is going to have to equal the velocity of the same belt that goes around this little pulley here. Now, this is pulley B here. For those of you that just tuned in, we're doing problem 1613. It's on page 332. But see, this can be written, see, that's RA. This can be written as RB omega B. Okay, let's put our numbers in. That's 75. Did they tell you what this omega? Yeah, they give it to you. It's 60 radians per second. That's nothings per second. And this one is 25. Oh, looky here. We can get the angular velocity of this pulley. Do you understand this little pulley here has been welded on? It's fixed to the big pulley here. So here's what omega B is going to be. It's going to be, well, I can do that in my head. I'm getting 180 radians per second. You do that too, and make sure that I did that right. Yeah, I did that right. So now we have the angular velocity of pulley B. It's all based on this simple idea that the velocity of the belt going around pulley A has to be the same velocity of the belt going around pulley B. That's the dirty little secret of how pulleys work. Okay, but we're not done yet. They got an air conditioning pulley. It comes over here someplace. There we go. Now the radius of this air conditioning pulley is 50 millimeters, and it's pulley C. And what they want to know for the answer is, what's the angular velocity of pulley C? Is that what they want? Let me read this. We're doing problem 1613. Yeah. Well, yeah. They want the angular velocity of B. Well, we got that. I did that. And then the angular velocity of the air conditioning pulley, C, we're going to have that. Well, here's how you get that. We got to get the velocity of this pulley here. See, this pulley is going around and around this way. And we know the angular velocity, it's omega B. Omega B. And see, so this pulley here is a velocity like that. We're going to call it, oh, I don't know, VB maybe. I think we'll call it VC. Just give it a name. And see that pulley has got a velocity here, same velocity. So we're going to write it. Here we go. The velocity of the pulley that's going around these two pulleys is equal to, in this case, it's omega B. It's R of B times omega B. And it's going to have to equal R of C times omega C. Because the belt has to have the same velocity going around those pulleys. It can't speed up. The belt doesn't speed up. It's got a constant velocity. Okay, now we know what this is. It's 100 millimeters. And we know what that omega B is. We got it right here. It's 180 radians per second. And we know what the radius is of this one. It's 50 millimeters. And so we can solve for the angular velocity of the pulley on the air conditioner. I can do that in my head. I'm getting 360 radians per second. If you don't believe me, plug it into your calculators for the air conditioning pulley. Now let's see how we did. This was problem 1613. And I'm going to look it up and see how we did. You can look that up in the back. I already did, and that's what they said it was. They said that the air conditioning pulley angular velocity is 360 radians per second. So we just did a pulley problem. Now, is there any question? Any question on how to deal with pulleys and their angular velocities? Well, I guess there's no question. Let's do a different problem. If you guys are happy with that, I'm going to erase it. We're going to do a different problem. All right. Okay, now this one's going to involve gears. I've got some gears here. Let's see. Yeah. Now this is problem 1620. It's on page 333. And it has an asterisk. Is that how you say it? Asterisk? Kind of a funny name. And it's got gears. And there's no answer in the back, but I got an answer book and I looked it up, and so I can tell you what the answer book says. But let's draw it here. There's a little gear. It's kind of hard for me to draw little gears, but I'm trying. See, they have teeth, see? And then there's a big gear. Oh, gee. That looks more like a pear or something than a gear, but we're trying. There we go. Now let's put some teeth on it. The thing is, these teeth need to be this evenly spaced, the same space between teeth. This is gear B and this is gear A. You want those teeth to mesh, to be the same distance apart. Here, let me see if I can show you. See, like these are the teeth. You want them to be to where they'll mesh like that. See, the same distance apart. And here's the dirty little secret of gears. The way they work is the velocity of these teeth on right here where they're meshing on the little gear, we'll call it VA, you want that to be the same velocity of the teeth on gear B. You don't want them to be different velocities. Here, let me show you what will happen. If the velocity of these teeth here are going faster, you're gonna break. You understand? You're gonna break some of those little teeth. You don't want to break any teeth. You want them to mesh. You want them to have the same speed. That's the dirty little secret of gears. I'll tell you another dirty little secret. The little gears always go faster than the big gears. The big gears go slower. It's just like if you ever watch, let's say somebody has a little dog, one of those little tiny miniature poodles, and then they have a Great Dane, okay? And they got them both on leashes and they're taking their two dogs for a walk. Well, the Great Dane, it takes big steps and it looks like it's going kind of slow, but it's going the same speed as the little dog. It's just that the little poodle, its feet are going so fast. Oh, those feet are going so fast on the little poodle. But on the Great Dane, it looks like he's going slow, but they're both going the same speed. The guy's taking them for a walk. The little dog's feet have to take more steps per minute, I guess you might say. That's the way it is with the little gear has to spin faster and the big gear spins slower. But they have the same velocity. Here's the equation. The velocity of A is equal to the radius of A times the omega of A. And that has to equal the same velocity of B. You don't want the teeth going different speeds. You want them to mesh. Mesh, M-E-S-H. You want the teeth to mesh. You want the teeth to mesh. And see, this is going to equal R of B omega B. Okay, well, let's see what they told us. They said here, the angular acceleration of A, let me write this down here. The angular acceleration of A is 4t cubed radians per second squared. Can you read my writing? There you go. where t is in seconds. If this gear is initially turning 20 radians per second, let me write that down. The initial angular velocity of A, that's the little pulley, is 20 radians per second, right? Yeah. They want to know the velocity of gear B. They want us to find the angular velocity of gear B at 2 seconds. That's what they want us to do. Now the radius of B is 0.15 meters, and the radius of A is 0.05 meters. Okay, so let's plug in our numbers here. The radius of A is 0.05 meters. And did they tell us the angular velocity of A? Yeah, it's 20 radians per second. Well, now wait a minute. That's the initial velocity of it. But we could go ahead and do that. Put in the 20, and we can get the initial velocity of B. See, now B has a radius of 0.15 meters. And what this is going to be is the initial velocity of, angular velocity of B. We might need that. I don't know. Can you do that in your head? I can't do that in my head. Let me get my calculator here. I'm going to shut up for a tiny minute. You got 30 seconds. I need the initial angular velocity of B, and I'll call on one of my excellent students here in just a minute. Okay, let me find one of my excellent students. Nicholas. Nicholas is in 4 of my classes, aren't you, Nicholas?
Just 3.
Oh, only 3. Oh, too bad. Nicholas, what'd you get for the initial angular velocity of gear B?
6.667
That's what I got.
radians a second.
Yeah, that's exactly what I got. Now that's the initial angular velocity. That's not what they want. They want to know the angular velocity of B after 2 seconds. Well, let me write an equation for you that you can't use. I need some room here. How about, here's some room up here. We all know it's October. We all know we're in dynamics. But we've got an equation like this. Now remember where this equation comes from. It's the rotational version of this equation here. And you need to just memorize that one, and that way you can write down the other one. But we can't use it here because this equation has got a skull and crossbones on it. Now back to Nicholas. I'm picking on Nicholas right now. Nicholas, why can't we use that equation for this problem to find the angular velocity of B at 2 seconds? Why is that, Nicholas?
Our angular acceleration is changing.
That's the problem. Nicholas understands. Nicholas understands. So you see this angular acceleration. Now, if it was constant, then you could use that equation, but it's not. So much for that equation. It's not going to work. Okay, back to Nicholas. If you don't have constant acceleration, what do you do? Got any ideas? Nicholas, what do you do?
Take an integral of something? No.
Yeah, that's right. You're absolutely right. You take the integral of something. Good going, Nicholas. Now here's your choices. There's really only three choices. One of them goes like this. One of them goes like this. And no, that's wrong. That was wrong. I caught it though. You don't get a thank you point. I caught that just barely in time. Now, those three equations, they're just the rotational version of equations that we know and love. Like, for instance, this one is the rotational version of, yeah, that's it. You all know that one. In fact, that's a definition. In fact, so is this. This is a definition. But see, if you know this one's pretty easy to come by. Now this one here, that's just the rotational version of at any point, if I lose you now, you speak up and ask me. You can ask me questions. And this one is the rotational version of yeah, there we go. And there's only three. There's only those three. And now Nicholas says we're going to have to take the integration of something. And so you just, you got three equations there. You just kind of fumble around and try some of them. You might try, well, I don't know. I don't know yet. And another little trick I think I showed you long ago is you can make a little table. There's some room here. But before we made a little table like this. I don't know if you guys remember doing that. But here, see, we don't have linear displacement, we have angular displacement. We don't have linear velocity, we have angular velocity. And we don't have linear acceleration, we have angular acceleration. And see, you can make a little table like that. And the thing is that at time zero, they give you, we'll assume that the wheel is at a zero angle, but it's got an angular velocity of 20. They said it did. But now wait a minute, that's A. That's A. Okay, is that right? Does A have 20? Yeah, I think so. We're really after B though, aren't we? Let me read this again here. Yeah, we're after B. So what's the angular velocity of B? Let's do B here. We're going to do B. B is 6 point blah, blah, blah. Now these are radians per second. These are, no, I'm sorry. Those are second, that's per seconds. And this is per seconds, radians per second squared. And these are nothings. Those are radians. And these are seconds. Right? Time is in seconds. Radians are in nothings. Angular velocity is in radians per second. Angular velocity is radians per second squared. Yeah, that's right. Great. I don't know what this is though, but I think we can get it. Let me make a little room here. I need some room. I was going to fill in this box here. See, they want the answer for when t is 2 seconds, I think. Isn't that what they want? Let me read it. Yeah, that's what they want. They want us to find this. Here, we'll put a little misty cloud right here. They're asking us to find the angular velocity when t is 2 seconds. Okay. Well, the angular acceleration of A is this here, but what's B? Let me think about this. Now, here's how it works. Linear acceleration is equal to angular acceleration times the radius. Another name for this is tangential acceleration, and you'll see in the flap of your book that equation. I'm trying to find it here. I don't see it. I don't see it. There it is. I found it. In the flap of your book, right where my thumb is wiggling. I don't know if you, in the flap of your book, there says AT equals alpha R. And here's the idea. The acceleration of the teeth in gear A had darn well better be the same as the linear acceleration of the teeth. See, the velocities of those teeth have got to be the same. You can't have those teeth going faster on one gear than the other, and same with the acceleration. So now let's put this in. We know what this is. It's 4t cubed, and this is 0.05 meters. And now we're going to get the acceleration of B, and this is 0.15 meters. So see, I can get the angular acceleration of B. I can do that in my head. Do you get a bunch of 3's t cubed for the angular acceleration of B? Plug it in your calculator. I think that's right. The thing, though, it's a variable. See, we can get it at time 0. Now let me see. I'm getting mixed up here. Well, at time zero, what is this at? Is this at, that's at any time whatsoever. At time zero, that would be zero, wouldn't it? I think it would. See here, when time is zero, you get a zero angular acceleration. But at time zero, this would be zero also. But see, it's a variable. Okay, well, we got the angular acceleration. Now what? Well, we need the angular velocity. That's what they're after of B. Well, we have those three equations. Those three equations are they're right here. Yeah, here they are. We don't need these anymore. Yeah, those are our three equations right there. We need one of these equations. And if you're trying to find the angular velocity of B, I wonder which one we would use. I like this one. Let's do that one. I just need some room to do it in. Is there any room over here? Can you guys see that? It's not very good. But here's the plan. Let's use this up here. This is brighter. I think you guys can see this. I don't think I need those two. I think I need that one. If it doesn't work, I'll use one of the other two. But look here, see if you can get to here with me. Because remember, Nicholas said we're going to have to integrate something. Can you get from here to here? Can you make it? Now we're going to integrate it. Here goes, Nicholas. Now here, we're going to have to go from 6.667 to some omega of B, which we don't know what it is. And here, we're going to have an integral going from 0 to 2 seconds of 1 point blah, 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 t cubed dt equal integral there we go. And we can solve that. What we've done is we've taken this equation and we've written an integral, and we can do it. I just need the room, that's all. Well, we got room over here. Let's make some more room. Now, when you integrate this, you'll get 1.333 t to the fourth over 4. All right? Yeah, from 0 to 2, we can do that, equals, well, this would be omega B minus the 6 point blah, blah, blah. Here's a nice equation. Now I'm going to shut up for a minute and a half. And I want you to take this equation here, and I want you to solve for this omega B that they want, the angular velocity of gear B. Go for it. I'm going to do it. You do it. And then I'm going to call on one of my excellent students. Okay, let me call on one of my excellent students here. Mark, unmute and say hello, please.
Hello.
Hello. Hey, Mark, did you, I got lost here. Hey, did you solve for the angular velocity of gear B?
Yeah, I'm not sure if I got the right thing, but yeah, I solved for it.
What'd you get, Mark?
Negative 1.335.
That's not what I got.
Oh wait, I made a mistake. Wait, 11 or 12 basically, 12.0.
Good going. That's what I got. I got the angular velocity of gear B at this particular instant in time at 2 seconds to be 12 radians per second. Now, I looked in the answer book in the back of this book, and that's what they said. So we did great. That was a little bit tricky, but we managed. We might have time for one more. Let's do one. Any question or comment? See, this is the dirty little secret of how gears work. The dirty little secret is the same business that R omega of one gear is going to equal R omega of the other gear. And see, if you took the derivative of both these equations, what you'll get is R alpha of the one gear is equal to R alpha of the other gear. And you see that those are based on, they're based on R theta is equal to R2 theta 2. They're based on the, what do they call that? The arc length equation or formula. That's the dirty little secret of gears. And just remember, the little gear has to have a bigger velocity Well, the little dog's legs have to go a whole lot faster. When I say velocity, I mean angular velocity. They have the same linear velocity. That the teeth of those two gears must have the same linear velocity. It's the angular velocity that the little gear has to have a much larger angular velocity. It has to spin faster. Okay, we got time maybe for one more. Any comments or questions? Now, there is some homework. I forget which one it is. You can look it up though. And you had your test. Most of you did pretty good. All right, well, I think we might have time to get started on one more. No, we don't have much time. I might only have time to outline this problem for you, but we'll do what we can. Now, this problem is problem 1623. Let me just outline the problem for you. We know something about gear A. The motor turns gear A with an angular acceleration of, it's constant, isn't that nice? When the angular velocity, and they give you that. They want the angular acceleration and angular velocity of gear D. Now, remember, Nicholas told us we had to integrate something to do that other problem. I don't think we need to integrate anything here because I think things are constant. It looks like the angular velocity is constant and the angular acceleration is constant. Okay. Now here's the plan. RA omega A is going to have to equal RB omega B. I'm looking at problem 1623. It's on page 334. This is the dirty little secret of solving gears. Now, it turns out that that gear C is turning at the same speed as gear B. So you could go the radius of gear C, but you get to use that same angular velocity of B because those are the same. Those, if you stare at that diagram, it's connected. And then finally, the RD omega of D. Now, what did they want us to find in this? Determine the angular acceleration and angular velocity of gear D. Okay. Well, it's the same stuff, guys. RA alpha of A should equal RB alpha of B equals RC alpha of B equals RD alpha of D. Now let's circle the stuff we know. They give us alpha of A. Let me circle that. What does it mean in my class when you circle something? And the angular velocity, they give you that, they give you this. Don't they give you all these radii? Yeah, look at here. They give you all of these radii. We know the radius of each one. No problema. Hey, look at here. If we know that and that and that, you can get that, can't you? And if we know all of that, you can get that, and you can get that. Hey, this is an easy problem, isn't it? Look, if you know that, that, and that, you can get that. You can get that. That problem is way too easy. If we had time, we could actually get the numbers, but we don't. Our time, it was short because of that power outage that went out, and we got a late start. But we'll put it on YouTube. Is there any comments or questions from anyone about today's lesson on what was it on? It was on pure rotational motion. And see, next time we'll get into combined motion, the exciting world when you combine rotation with translation. Any last words? This is it. Here's your chance. Speak up. Okay. Well, good going, students. Bye-bye for now. See you next time. Ta-ta.
Sir.
Be good. Ta-ta.